Okay, see the chemistry behind what we are saying. You see here, this is the iodine dissolving in potassium iodide to give you potassium triiodide. Then, in this reaction, I want us to understand this aspect first before coming to the calculation, for us to understand why that 25.4 grams of iodine will not dissolve in 6 grams of potassium iodide. First, let's see this type. In this case, this triiodide, by structure, you only have potassium plus bonded to 1, 2, 3. That's the triiodide. It's only one that is negative, whereby this 2 is still in form of elemental iodine. Seeing how the triiodide is formed, it's just one molecule of iodine being, there is a kind of a complex ion formation here, and this reaction here is just showing Lewis acid and base reacting. If you know about Lewis and Lewis acid and base theory, you understand here. One is acting as a proton donor, electron pair donor, the other is accepting. But what matters is this is the I3, which is reddish brown. But out of this I3, this 2 iodine is still free. This one is not free to be reacting with anything like sodium thiosulfate. Do you get what I'm saying? This I is colorless. This is the one that is that reddish brown, or the red color in concentrated form. So in our calculation, if they give you if they tell you any given amount of iodine to dissolve in potassium iodide, this iodine do not contribute in the one that will be neutralized, because you can't convert what is already in iodide form to iodide again. And the equation of the reaction from this titration is just that sodium thiosulfate is reacting with this iodine, converting this elemental iodine to sodium iodide, which have this ion here. So that's just better. Now, coming to theoretically tell us what is going to be the perfect endpoint in reasons. If you have 254, this is this. 127 times 2 is 254, which will now require 166 grams according to this equation. 166 grams, that's the molar mass of potassium iodide, to completely dissolve 254 grams. So if this equation is correct, of which I know is correct, by this mole ratio is 1:1, which means by mass is 254 grams of iodine will be dissolved by 166 grams of potassium iodide. Therefore, 25.4 grams of iodine, which is what they provided for us, will require what mass of potassium iodide? Automatically will require X. When you cross multiply, you find out that X will be equal to 66.6 grams. So WAEC is supposed to provide for us at least 16.6 grams, not 66. They're supposed to tell us to use 16.6 grams against 25.4 and not 6 grams. Therefore, you find out that the whole mass of the 25.4 will not dissolve. And mathematically calculating this, you discover that if 16.6 grams of potassium iodide is required to dissolve 25.4 grams, that is the correct thing that they're supposed to provide. But unfortunately, they provided 6 grams. So you can now assess how many molecules of the iodine is dissolving. So, and this equation is very correct because we have done the practical. We discovered that the whole iodine is not dissolving, and this is the reason why. If you do this calculation, you get that this should be X, cross multiply. I think I don't have my calculator here, but I've done this. It will get you to something like 9.18 or 9.2. So you find out that out of the 25.4 grams provided, that about 9 is going to be only about X will be about 9.2. Let me take it in that range. And 9.2 grams of iodine is going to represent what in mole? For you to get the mole, it will be 9.2 divided by 254. And when you do this, let me get my calculator. Okay, 9.2 over 254, 9.2 over 254 will give you about 0.0362. So this is the mole. This is the highest concentration we can get by dissolving 25.4 grams of iodine crystal in 6 grams of potassium iodide. And when this is our Ca, if we put B in burette and titrate against A, the theoretical endpoint, if we use 25 cm³ portions of A, the theoretical endpoint should be 18 automatically, but unfortunately we are getting something like 6, 8, 10, and somebody like us even getting lower than 6. What's the reason? The reason is because the iodine itself, out of this 9.2, the triiodide, inside this triiodide we are seeing here, This 2 that is still elemental iodine is still subliming, so which means it's still unstable. Some mass of it is getting lost. So we are losing mass even when it is still in this solution form, in form of triiodide, because the iodide ion like this doesn't sublime and is colorless. It is this free elemental iodine that is giving it that reddish brown, and it is subliming, lessening the mass, which will make you eventually end up with something less than 9.2. But all things being equal, theoretically from what they gave us, if they put B in burette and tell us to titrate against A, which is iodine, our endpoint theoretically should be 18. So let's see how it is 18. Okay, putting the B in burette, titrating against A, which is iodine, that's the most likely question. That's question 5 in our likely question 5. You will see that there is the Ca here is the 0.036, of which I have proven how we got. Then times 25 here, this VA. If B is in burette, our VA now becomes volume of pipette, which is 25 cm cube. Then the concentration of the B used was 0.1. That's why they told us to measure 24.82 grams and dissolve in 1 dm cube of solution. I know the 24.82 is for hydrated. If you analyze it, it will still represent 0.1 mole of the anhydrous, because water is not the thing that is reacting with this iodine, rather is the sodium thiosulfate. So 0.1 mole per dm cube hydrated form, which is represented by mass 24.8, is also equal to 15.8 grams of anhydrous, which is still 0.1. Then VB here is our endpoint, since it's in burette. So equal to 1/2, which is the mole ratio of the acid, the mole ratio of the iodine over the thiosulfate ion. Then after everything, you find out that the VB will be theoretically 18, theoretically. So if you want to use, if they tell us to put B in burette and titrate against titrate against A, which makes work easier for the students, there won't be dilution, you can now forge your endpoint around this 18. Yes, of course, we are going to assume everything happened correctly. So you now tell your students that endpoints, don't use anything less than, you can use anything from 15, 12, because they are assuming that the iodine did not sublime all that too well. Anything, let me just say 12 to 18 is allowed. But I told you why you are able to get that 8, which is very far from 18, or even get that 6 or 10, because of the fact that even the triiodide, the free elemental iodine, there still sublime, and when it sublimes, the mass is lost. Secondly, some of our sodium thiosulfates are not pure. So because of that, these are the reasons why we are getting something not up to 18 theoretically. But if all things becomes equal, and again, the potassium iodide you buy, some of them are not also pure. And when the potassium iodide is not pure, it means that 6 grams you are measuring will not take up to 9.2 grams of iodine, which will not get the concentration up to 0.036. So this is the conviction here. We are going to work on our endpoint if B is in burette and A is in conical flask without diluting any of them. You work around endpoint from 12 to 18. Don't exceed 18. Don't you ever try that, because this is only when there is no sublimation. That's why you can start from 12. So theoretically, if B is in burette and A is pipetted inside conical flask, our endpoint should start from 12, from the range of 12. Or you can even, somebody like me, normally even if you use 10, it can be accepted. But going above 18 is a lie. Getting 18 point something shows you are lying, because there is no way you'll even get to the 18 because of the fact that the iodine sublimes. This is only achievable if you displace the iodine immediately before titrating, not when it's already in elemental form. As you're even weighing it, before you dissolve it, some mass are lost, actually. If you try this thing I'm saying, you put iodine in a weighing balance, check your time, the one that have sensitivity of 0.01, you find out that within 5 minutes you have lost a considerable mass. The one like weighing balance that have the precision of 0.01, able to measure it in 5 minutes, you see the mass lost. It's going to read, the weighing balance will change, and that tells you the rate at which iodine sublimes. So this is it for the endpoints. I've actually attended to this endpoint if B is in burette. So if they put A in burette as we are suspecting, I told you the only condition is that they must dilute that B up to 10 times before they put A in a burette, and we are looking at our endpoint, or they dilute up to 5 times either, 5 times and above. So your endpoint will now be a kind of steady 20, 22, 24, within that range.